So one section of system level tuning that kind of deserves a mention all by itself is Readahead, for a couple of reasons. One, it is important to have the correct Readahead settings, but also because it's one of the more misunderstood things that people tune. If you go out and read about Readahead on the internet, you'll find varying different pieces of advice, sometimes even conflicting pieces of advice. So before we get into what that advice might be, let's actually talk about what does Readahead mean. So when the kernel is actually requesting a page from disk, this presents, as most things in Linux do, as part of the file system itself. In /dev SDA, for example, this would be the first SCSI or SATA device that was detected when this operating system was installed and booted up. So this block device dev SDA, the kernel's decided, or a process decided, and asked the kernel for a particular page off the disk, please. So that's a 4K page. 4096 bytes has been requested from this particular disk. Now if you remember back to when we talked about spinning disks, the seek time, the time it takes to actually get to where the data lives on a disk, is generally considered quite expensive, particularly if you're going to be doing a lot of it and it's non-sequential. So from that perspective, when you've got an expensive thing like a disk seek in play, it makes a lot of sense that if a single 4K page is requested off the disk, then when you actually get to the sector on the disk, instead of just reading that 4K, let's add on some amount additionally, and we'll read that into the file system cache while we're there. That makes a lot of sense. If the expensive part is actually getting there, and there's any chance that this extra data that you're going to read in is going to be relevant in the future, then reading it in while you're at that particular part of the disk makes a lot of sense from an efficiency perspective. So if you've got good data locality, if you're likely to, after you've requested this first page, if the second page that you request after this, in terms of a sequence in time, the second page request that comes in here, if that is going to be part of this extra piece that you read in, there's no need to hit the disk again. So the second page has already been read in as part of this extra piece that you've read in, so it's like, oh, that's already there. That's basically a soft page fault instead of a hard page fault, and you've saved having to seek back to that part of the disk, and you free up the disk head to go and do the next read from somewhere else. So you can see the kind of logic behind doing this while you're there, and the Linux kernel actually does do this. So the setting that controls how much and what size X actually is Readahead. So therefore, Readahead is the number of extra sectors to be read in for any disk access. Now I've underlined sectors here because it's often misconstrued that Readahead is actually the number of kilobytes to be read in for any particular disk access. It's not. It's actually the number of sectors. So let's quickly take a look at an example of what Readahead looks like. So when you want to find out what Readahead actually looks like for a particular device, you run this command, blockdev, block device, -- report. And you will need root privileges usually to get any meaningful output out of this. We've only got one disk, XVDA1, so this is a device that's presented through the Zen hypervisor. That's what the XVD piece usually means. If this was an S, it would be a local SCSI or SATA disk. And the interesting value here is this RA. This is Readahead. RA is Readahead. And actually SSC is sector size, which will come into play as well. But RA is 256. So an RA setting of 256, if we go back to here, so RA equals 256. That implies 256 by 512 byte sectors should be read in addition to whatever was actually requested, right? So that means that for every 4K page, if you request a 4K page off that disk, you're going to get the 4K page, but you're also going to get 128 kilobytes of extra data. Now, where does that go? That goes into your file system cache, which you may remember from our earlier experiments was where most of our data was going to end up with the touch command. It was also where the data was going to end up if we did a process restart and the data was still in the file system cache, but wasn't assigned specifically to MongoD. So the file system cache has come up a few times since then. That's where this data will go. Now, if you have good locality, then the next page that you're going to read is a high probability of being in this 128 kilobytes. However, for the most part, the data access pattern in MongoDB does not guarantee good data locality. The exceptions being the oplog, or more generically, capt collections. So if you're reading from capt collections, reading from the oplog, most likely after you read one piece of data out of the op log, you're going to read the next one and the next one and the next one. You're going to be iterating through it, things like that. So in those scenarios, you are going to get decent locality, and so a high read ahead setting would actually be beneficial. And this is also similar for most relational databases. They attempt to write indexes and most of their data sequentially so that it can be retrieved in this manner. So if you have this, you have good data locality, a good chance of actually getting the next requested piece of data in this 128 kilobytes, you might actually want to increase read ahead for this sequential type of access. This assumes a couple of things. First of all, it assumes good locality, which we've already covered. There's a couple of scenarios that you get good data locality with MongoDB. However, it also assumes that seeks are expensive. And for the last 30 or 40 years, that has always been true, until very recently with the advent of SSDs, which we covered earlier. Solid-state disks mean that the seek expense of getting to a particular point on disk essentially goes away, or at least is basically the same no matter where you're actually requesting the data from. So data locality and the amount of seeking that's involved is no longer as much of a consideration on SSDs. So, if you have SSDs, or you have a random access data pattern, it becomes less obvious if read ahead is actually of benefit to you. The random access data pattern means that, oh yes, you're reading more data into RAM, but the likelihood of it actually being of benefit to you is quite low. So, from that perspective, a high read ahead setting doesn't seem to make much sense. And in fact, putting lots of data into the file system cache is going to evict other data. There's only so much room. It's a limited resource. So you can imagine, if we've got our physical RAM, here's the system stuff, we'll just do that in red. You can imagine that by putting all this data into the file system cache is going to grow. It's going to get bigger. And the system stuff is unlikely to be paged out, so what's going to get paged out is more MongoDB data. Now, if you've got good data locality, in all likelihood you're going to use that data that's been brought in by Readahead, that 128K that we had on the previous screen. If that's getting loaded in the FS cache and it's growing and you are eventually going to use it, then all that will happen is a soft page fault and the green will be assigned over to the blue, no harm, no foul. However, if that 128K that's come in with the page that you actually asked for is not MongoDB data, or it's not relevant MongoDB data, you have poor data locality there, then all that's going to do is reduce the amount of RAM that you've got available for what it would be your working set in this case. The MongoDB data that's active in RAM will experience pressure from this file system cache as you're loading in that extra data as part of the read ahead process. So if memory efficiency, in other words keeping your working set in memory, is your priority, and in most cases it's going to be, you're going to want to actually have a lower read ahead setting. So you've got a random access data pattern, maybe you've got SSDs or maybe you don't have SSDs, but you have a priority for memory efficiency. You want to get as much data and as many indexes into RAM, into active memory as you can to keep up your performance levels. So if you've got that priority where you have SSDs, random access data pattern, you're hitting all over the disk, as it were, then you're going to want a lower read ahead. The question then becomes, how low? And the answer to that question is there is a lower bound. When you create an index in MongoDB, the index buckets, sort of the smallest piece you're going to be scanning in when you're scanning through an index, is 8K. That translates to 16 sectors. So you'd want to keep your read ahead setting approximately one index bucket at least in size. And the likelihood is that you're going to get more than one of those sequentially. A lot of the index builds are going to go on and they'll be close together. So generally what we'll actually say, 16 sectors is your lower bound with 32 sectors as your recommended setting there. And again, that is if you've got random access data pattern priority for memory efficiency over paging in things off disk more quickly, and in particular if you've got SSDs, you're going to lower your read ahead, you're going to want to bring it down to 32 and have a nice efficient method of paging things in from disk without filling up that file system cache.